right. Can you hear me?
Yes.
All right. Well, then, let's start. And how are you doing?
Doing pretty good.
Good, good. All right, so we'll continue the discussion of mechanics for some time now. And, well, a couple of lectures actually on it. And again, any questions you have, please ask and so forth. So please make it more like a dialogue. Otherwise, it's boring. So what we have so far? So far, just considering some sort of ideal situation. You remember empty space and blah, blah, blah. We figure out that there should be some law of motion. This one, right? It's a hypothesis according to our construction, but you know, well, we know that it's correct. I mean, I did that construction sort of because I knew where I was going for. It's a lot more difficult. It was a lot more difficult for people like Newton. Well, think about it. It's actually quite a difficult story for him. What I described to you, and the empty universe, right, with just one particle and the observer, or two observers, two particles, one observer, and like trying to match what the intuition with what we can write. That's sort of one of the plausible ideas, which hypothesis which can appear in there. That's the only thing which I do, which I did. But for people like Newton, it was actually quite difficult even to start thinking like that, because empty universe for Newton made no sense whatsoever. And I don't believe that what I described to you it was his way of thinking. He probably did it somehow else, somewhere else, and I don't know what. It's exactly a mystery. But for him, empty universe did not exist at all. And he was a very religious man. Majority of his works actually on religion, not on physics. And so for him, empty universe that didn't exist, right? And it was unthinkable to think about it. So anyway, he somehow managed to write it, and it was the start of all the mechanics which we know. And he also did a lot of other things about light and so forth, which also are quite important. And but that's what the first thing which you come around when you see when you study physics. Now this A is what is called acceleration, right? It's the rate of change of velocity. Right, this is our A. Right, and the velocity is the rate of change of the position. Velocity dr over dt. Right. So r is the vector. We need to we can describe position by a vector, right? By three numbers, and those numbers change. So the vector is changing with time, and the rate of change of that vector, right, is called velocity, and it is a velocity, right? And the rate of change of the velocity is called acceleration. So that's what we have, and m is just a number which characterizes like any particular object. It's called its mass, or its inertial mass, to be more precise. And then there is one more letter here, that F here. And this is the most mysterious letter. In fact, everything else is sort of defined quite well. I mean, the acceleration is defined, and m is just a coefficient of proportionality which should be measured, and it depends on which object. It describes the object, right, how it moves. But what is F? Well, F is a force, right? And we sort of intuitively understand what force is. If somebody's pushing you right out of the way, and you feel some force acting on it, or you, I don't know, hammer a nail down and you apply some force to it, and so forth. So it's somewhat intuitively clear because it's been used in your life for quite a long time to describe different situations. But that's not enough. We actually need to know something about that force, that letter F. What exactly does it mean? And So the force, as I said, it's a mysterious thing, and in many senses, and it's sort of a vector quantity which describes interaction. That's the only thing which we can say about it. So the force, if we have two particles and they interact with each other, we can say that they apply force to each other, and that force is of course equal in opposite direction, applied to different points, to different objects, and so forth. But how can we be sure that every interaction can be described by just one vector quantity? It's kind of strange question because that's how it looks like, right? From intuitively, from our intuition. If I push something, I push it in some particular direction with some particular magnitude, right? And so it has the direction and magnitude, so it should be a vector. But it's not enough to be a vector, right? It's something which has a direction is not necessarily a vector. A vector is would be the following. So if we have one point here, and it interacts with 2 points. So this is point 1, this is 2 and 3, right? So if I write all the forces which act on point 1, then there is one force which is going from interaction with point 2, right? This one. And there is another force, interaction with point 3, object 3, which is F1 from interaction with object 3, right? That makes sense?
Yes.
Yes.
Yep.
So in order for the force to be vector, we should be able to write that there is a total force which is sum of all those 2 forces, right? So there is a total force F, which is vector sum. This is total force which acts on point on object 1, which is sum of the 2, vector sum of the 2, right? And it's not clear that it should be. Why it's like that? Why not? There is no some sort of coefficients here, and how is it possible always to define the interaction in terms of vectors, which then will sum up like that? Because those interactions can be completely different nature, right? One interaction, let's say from point 2 to point 1, can be electrostatic interaction, right? They have charges to point. And the other point, and 3 to 1 can be, I don't know, gravity, right? And those are completely different in nature forces, interactions. And yet we claim that their action is just a force, and those 2 forces just sum up, and that's it. We just sum up vector force. This is not clear why it is so, why it should be so. Yet we know that it is, and well, and only if it is so that all interaction can be described with vectors, right? Only then we can actually write something like F equals ma, because it is definitely a vector. A is a vector. It's defined as a vector. Vector differentiated twice with respect to time. Time is the scalar, so it's a vector. So on the right hand side here is a vector. So on the left hand side, it must be a vector, right? A vector cannot be equal to something which is not a vector, right? So it must be a vector. So it must have that property of summing up. But how do our interactions know about it is absolutely not clear. And of course, it means that it must be checked by experiment. And it turns out that we actually can, every interaction, it is possible to describe with some vector quantity, which can be called force and which is a vector. It's an experimental fact. So it's then everything makes sense. And so we have some force, and the total force is just sum of all forces. And then that's it. And then knowing all forces, if we know all the interactions, right, then we can write the equations of motion for that particular point, like object. Now, then of course the next question is where those forces come from? How do we describe the interaction? And that's basically the rest of physics is what we do. And so there, we just can list all the forces. Fortunately, it's only 5 of them, fundamental forces which act on which can describe interaction. It's electromagnetism, gravity, and weak and strong interaction. There is nothing else. Electric, magnetic force, gravity, weak and strong interaction. And that's it. That's all the forces, all fundamental forces. Turns out that only 5 of them, and all 5 of them can be described by this equation. Well, it's a little bit of a lie, because if you try to use this equation in quantum mechanics, it's incredibly difficult. It's actually impossible, in fact, because of the reasons I told you, that letter F is not very well defined, and in quantum mechanics it cannot be extended to quantum mechanics. It also that our intuition about the forces cannot be extended to special or general relativity. We have to invent something else to describe interaction, and we will actually today. It's simply looking equation, but it does have some problems with it, and namely this one. Okay, so there's a couple more.
Dr. Abinov?
Yes.
So I assume that like probably the solution to the dilemma of F not being defined would be kind of dealing with the energy sides more, because of how it can translate from one type of representation to another, since we're just because it's energy.
Yes, that's actually correct, and that's exactly what I'm going to do today. But it requires some restrictions. Okay, let me just say it. If you already understand what I'm talking about, that's actually better. So it's only possible to describe forces with energies, with what is called potential energy of interaction. Only possible if all forces are conservative forces. What is conservative forces? I'm going to talk about, but arbitrary forces is not a conservative force. It's a huge restriction of what kind of forces can exist, right? And it turns out that all our 5 fundamental forces are actually conservative forces. But not all the forces which you have to deal with are conservative forces. For example, friction is the most complicated part of physics, in fact. But friction is not a conservative force by any means. It doesn't conserve it, right? And so it's actually quite an interesting question, which I will discuss a little later, how non-conservative forces can appear if all fundamental forces are conservative. It's an interesting and quite non-trivial problem, in fact. But it exists. So when you're dealing with, I don't know, with typical mechanical situation, I don't know, with throwing balls or whatever, describing some machines and stuff like that, you have to deal with non-conservative forces. They're called friction, right? Typically. And in that case, you cannot describe those forces with energy. You have to deal with forces, right? And so we don't want to restrict ourselves in dealing with only conservative forces. But if you want to study fundamentals of the fundamental laws of physics, then it's actually quite interesting. It actually does work. So all the fundamental forces are conservative.
Dr. Abinov?
Yeah.
So would that mean like if we were dealing at the atomic level, we would have to deal in forces as well, even though you said that kind of conflicts with quantum mechanics?
That's you see that in quantum mechanics everything is much simpler than in classical mechanics. Quantum mechanics is much simpler than classical mechanics. I understand that it can be surprising, but it is, and it's mathematically more difficult. There are partial differential equations instead of ordinary differential equations. But conceptually, it's very, very counterintuitive. But if you learn how to deal with it, if you do some intuition, it actually becomes simpler than classical.
But you can deal with non-conservative forces at that level?
It's a very difficult problem. In quantum mechanics, there are situations where forces are not conservative. You actually have to derive them from conservative forces. All fundamental forces are conservative. How a non-conservative force appears out of conservative ones, it's actually quite a non-trivial problem. And in every time we have something like that, well, we know how to solve those, where they appear in some particular situation. But it's people still are working on them, and they still find some new results because it's a very, very non-trivial problem. Again, I'll discuss it where it comes from and how, what is the route to take it, but a little bit later, right? So in quantum mechanics, you sometimes you are dealing with non-conservative forces, and it's always a mess. It's always have some tricks, and your intuition doesn't work, and so forth. And it's exactly the same because you cannot use this for quantum mechanics. All right. So, well, first of all, let me point out something which missed in many cases by students in this situation. So let's consider a trajectory. So let's say the particle is moving and there are some forces acting on it, and it's moving in some trajectory from one point to another. Okay, and so we can see that we can draw a tangential vector to any point. So this is a point that there is a tangential vector of the trajectory, right? So this tangential vector is parallel to the vector of velocity at this point, right? Because that's exactly what vector of velocity is. Vector of velocity tells you how the position changes in infinitesimally short time, right? There is infinitesimal interval, and here's your change of your position, but that's exactly how a tangential vector is defined. Right? You take two nearby points and you draw a vector which is going from one to another, and then take two nearby points closer and closer to each other. So the vector which is velocity is always, by definition, it's a vector tangential to the trajectory. Okay, it's a vector of velocity, right? Vector of acceleration is almost never tangential to trajectory. In particular, in this case, you see that I had this vector here, so my vector of acceleration will be something like this. Right? But vector of acceleration is exactly proportional to the vector of velocity of force. So in this particular trajectory, I know that the force must be something like this. Must have this direction. You see that the vector of force and the vector of velocity or trajectory, right, or direction of the trajectory, they almost never coincide with each other. Right. So, for example, if you have a particle in electric field, you can draw that electric field lines, right? Remember those? That was the question, by the way.
Yes.
So that's those electric field lines. Electric field lines are such lines that the electric force or electric field, right, is tangential to those lines. This is my electric field. Let me use another. This is my electric field, right, at every point. But electric field is a force which acts on the particle, right? So the trajectory of the particle in this electric field will not coincide with those electric field lines. It will be something like that. It can be anything. It has to be a solution of differential equations, but you cannot just look on electric field lines or electric force lines, right? You cannot say what trajectory will be. Right? Trajectory does not coincide with force line. Trajectory must be calculated because this is a differential equation. Remember that? So that leads to a lot of that simple thing leads to a lot of confusion because in many cases, what students do, they draw, let's say, electric field lines, and then they because it's already lines are already drawn, right? They assume that those will be trajectories of particles in that field. That's almost never correct. There are some special situations where it is indeed so, but it's a very, very, very special situation where very specific initial conditions, very specific form of electric field lines and so forth. So it's very unlikely than in any non-specifically designed problem that will stand, right? So trajectory is not electric field lines. Please remember that. All right. So let me remind you again that this is, because of all those definitions, this is actually a differential equation of second order, typically nonlinear differential equation. So just plug in velocity here and then acceleration in the Newton's law. What I will have, m dr over dt, the second derivative, right, equals vector m. That's what it is. Now, what does that mean? It means that in every point of space, in every moment of time, if your particle is moving, if your particle of mass m is moving, right, and that particle at this particular moment of time is in this particular point of space, right, then the acceleration of that particle will be equal to the force at exactly the same time and exactly the same point of space. The force can be different in different points of space, right? Think about electric field, right? If you have electric field and you put a test charge with some particular charge inside it, then the force which acts on that particular charge depends on where it is. If it's in one point, it's one direction. If it's some other point, it's some other direction and magnitude. So the force depends where the point is, right? So the motion of the acceleration of the particle at this particular moment of time and this particular moment point of space where the particle is right now, right, depends on the force at exactly the same point of time and space. Now, after that, it's acceleration, right? It has velocity, so we need to solve this equation. We can find where is the particle will be in the next point of time. It will be somewhere here, for example, right? And then the next moment of time, so it is here. Even if force does not depend on time explicitly, right? Your point at which you need to find that force has changed. So the value of that vector, the force, will change, and it will be something here at this point. So at this point of space or at this point of time, because that's where the particle is seated in this particular point of time. And then you have to do it like step by step and compute all the times of accelerations and every point of space and so on. Okay? Does it make sense?
Yes.
Yes.
So that's why it's a differential equation. It's not. It must be solved as differential equation. So it must be supplied with initial conditions, and that's actually a good thing, right? Because then that's what corresponds to our intuition. That also, for example, think about it. If I throw a ball, right, and I want that ball to get into a hoop, right? So what do I need to know in order to throw it this way? Well, I need to know my initial position, where I'm throwing it, right? It's a completely different story if I throw it right next to the hoop, of from Houston, right? That's one thing. And second, I need to know where and with how fast must be initial velocity, right? Where do I throw it? What is the direction do I throw it? And with what velocity do I throw it? Right? Those two things completely define the future trajectory, and that trajectory either goes to the hoop or it misses. It misses for me. But that's so every trajectory is defined by the force field which acts on that object. And in case of balls, this is gravitational field. And our initial position and initial velocity. So force field is something which is staying here, and initial position and initial velocity are the initial conditions for those differential equations. For this differential equation. Does that make sense?
Yeah.
So that's exactly what you've been doing in the introductory classes when you were considering just a simple force field, right? Which does not depend on anything. It's just mg y minus, right? This is my force. Vector force, y with a hat, usually hat means unit vector in direction of y. So it has no units, nothing, it just tells me the direction. Oh, that's a particular point. In this particular case, this y is pointing up and its value is 1. Right, so that's my force field, and then I write equations that m, and if it only moves along y direction, then dy second derivative of the position, which is coordinate y, right, must be equal to minus mg. Right. So then I solve this equation and I find that the solution depends on two arbitrary constants, right? It's y equals y naught plus v naught t plus g t squared over 2. And those two initial conditions which I need to have in order to completely specify my motion. Initial position and initial velocity. Exactly as we expect, right? Does that make sense?
Yes.
No, sorry, it's minus. Because of that minus. That make sense?
Yep.
Yeah.
All right. So, but again, I really want to emphasize that it's only correct. That solution only works if you have a force which does not depend on anything, neither on time nor on coordinate. In every point of space and every moment of time, it is the same force going the same direction, the same magnitude. Force is a vector, so we must specify direction and magnitude. When I say the same force, it means the same magnitude and the same direction. Don't forget about direction. Okay. Right? So this is only specific for this very, very, very specific and extremely artificial situation when force does not depend on neither on coordinate nor on time. Right? It almost never this way. You have to work really hard to make it to make such a force field, and because simply there is always air resistance, right? And then everything you need to add the force of air resistance here, and that air resistance depends on velocity. Then velocity is the first derivative of dy over dt, and so forth. And you need to then solve the differential equation in U and so forth. Right? So it's always and that in any extended area or distances like that force is not necessarily constant with respect to coordinates, right? Because we know that the Earth is here, right? So the force here and the force here, although they may have almost the same magnitude, they definitely have different directions. Right? So the force then is not a constant as function of coordinates. So there are only very, very limited situations when you can use those that kind of equation, and but that again that's the simplest one, the simplest case, and it doesn't involve really solving much of the equations, and that's why they teach you that those in introductory physics, because otherwise you would be overwhelmed with all the math which involved here, and that's really not the point. By the way, it's also not the point to me. I have in homeworks, I have some, you need to take, once in a while, you will have to take some integral. I don't care how you take the integral, right? If you ask your friend ask Google, use Mathematica, and whatever. It's all fine. I'm not teaching you how to compute integrals, right? And I want you to understand physics behind them. I don't want you to get bogged down by math. So don't fret about it. If you have Mathematica, you just plug it in and gives the answer. It's all good. Just say that it's coming from Mathematica, and so I wouldn't look for your solution. Anyway, that's what I do, right? I remember that when like it was like about 30 years ago when I became a graduate student here. I used to do this. It was not Mathematica; it was Maple back then. Almost the same thing. It still exists, but Mathematica is much more popular now. And I used to have a race with that Maple. I would take an integral, I give it to Maple, and then take it by hand. And about half of the time, I would win. Now it's impossible. And those things become so much better that it's much easier to actually do it. But anyway, so let's continue discussing. So what do we have now? If you think about it, one of the fundamental forces, well, two fundamental forces which you're familiar with, well, actually familiar with three, but anyway, it's electrostatic force, right, between charges, and gravity. And in all of those cases, right, if you have some electric field, and let's say that electric field is produced by some static charges. So you have some big charges somewhere, they produce electric field. Now you take a test charge, you put it in that field, and you kick it, right? And you want to, so you give it some initial position and initial velocity, right? That's initial conditions. And it starts moving in that electric field. Then what we have? The same as gravity, right? It's the same story. That's something which I try to emphasize, that the nature of this force, of this motion, the nature of this force doesn't matter. All the interactions, no matter what they are, they produce something which is called force. And if you know that force, that's enough. You don't care where it comes from. So, but in both cases, electrostatics and the gravity, what we have is a force field, right? What you have, let me draw it in 2 dimensions simply because it's easier to draw in 2 dimensions. And what it means is that in every point of space you have a vector, right, which is force. And that vector depends on on the position, right? But in every point of space, if you take a test charge, and this is electrostatic force, right? You plug it in here, you put it in here, there will be some force acting on it. You put it in here, there will be another force acting on it, right? So in every point of space, you do have this field, right? So you actually, force then is described by a vector field, force field, right? Sounds familiar? And so it's a force field which is produced by either charge or gravity. Now, how it produces, what it means, and it's a different subject. We'll study it later. But for now, it's all what's important is that in every point of space there is a vector of force. Right. So then, in this equation, what we have is that vector f depends on the position. Right. And that would be our equation. It turns out that equation, just written like that, has some specific properties. And let me start discussing that property with this equation. Do you know what mechanical work is? Well, you should. It was in your first homework. Do you or do you not?
Mechanical work, you said?
Yeah, work in mechanics.
Isn't that just the change between the potential and kinetic energies?
No,
or is it
work by force, right? You need to start this definition. So you have some force, and then what is the work of the
Just the force dotted with the path it takes, or integrated, of course.
Exactly, yes. So it's a very common, again, it's a very common thing which students write that force equals F times distance. Force times distance, right? Again, this is unfortunate consequence of the fact that we need to teach physics to students who don't know math. There's a lot of math later in life. And so this is, of course, very, very limited definition. Because what is, so that distance which we have here is a finite distance, right? This is distance. And the force, well, first of all, it can have different directions here, and it has also different magnitudes. So then, what do I put there is not clear. It's a bad definition. It doesn't tell me what to do. And all the mathematical definitions, all the mathematical formulas tell you what to do. If I don't know what to do in this situation, it means that it's bad definition. So when force changing with distance or with time, whatever, it's actually that definition cannot work. I don't know what to do. So instead of that, what we can do is to say that we write the increment of work. The increment of work equals the force which acts of work done by this force, right? It's important which force is doing work. So that increment of work equals the force at this particular position times the change dot with change of distance. So I cannot use F and D or F dot D, right? When D is finite and it's long. But when I have some infinitesimally small displacement, dr, right? Then my force field is pretty much the same in over every point here. Well, unless I have actually some singularities of my force field, but we neglect those. And so my force is pretty much the same on on infinitesimally small interval, infinitesimally small displacement. And when I take the length of the displacement smaller and smaller, the force along this displacement will be more and more uniform, right? It will be pretty much the same. The difference between forces in different points of the space will be negligible. So for infinitesimally small displacement, I actually can define this. Right? And then if I have a path, my object is moving along some path, and I have forces acting, some force acting on it, there can be some other forces acting on it also. But I'm only consider one particular force. Right? Then work which is done by that force, total work which is done by that force, equals just sum of all the increments. F dot dr summed, right? All of those increments summed over my path gamma. This is my path gamma. Right? Does that make sense?
Yep.
Yeah, that makes sense.
Yeah, so then in this definition, that actually I know what to do, because that exactly tells me what to do. I need to take my path gamma, right, which is given to me. Say again? I need to take this gamma, split it on little pieces. In each piece, I have some force, and I multiply that little increment displacement, little vector. I dot product. I take the dot product of this little displacement with the force, and then I sum up along the path, right? So, but notice I must know path in order to do that. So if I change path, although I can keep the initial and final point the same, remember that it's actually there are some other forces can be acting. I'm only considering the work on some particular force. I said there is gravity and there is electrostatics, or I'm moving particle myself, and there is also electrostatic force. So I'm computing the work which is done by electrostatic. But I am actually moving the point along the object along the path. then the work along this path will be different, presumably, right? Because the path is changing, so now I need to take it bit by bit again, and then all of those displacements are different on this path with respect to this one, and all forces in all points are different, right? So all the dot products will be different for each of those little increments, and then I sum them up. I sum up different numbers. Well, I presumably will get different results. So the work will depend on path, and it's typical situation. It's the force. If we try to find the work, we need to know path in order to find the work done by a force. Okay?
Dr. Ivanov?
Yes.
So I'm aware that like check out for it being conservative forces, or if it's to basically that the work is independent of the path is by what we were discussing last time.
Yes.
But as we're like, how does the intuition build on the how do I say this? When you're just looking at the scope of the problem and you're kind of able to gauge already if it's going to be conservative or not. Is it just kind of building as you do more problems, or is there another way that physicists will like look and be able to gauge the problem, I guess?
Yeah, I mean, first of all intuitions are built by solving problems. There is no other way. The only way to build an intuition is to solve a bunch of problems. The more problems you solve, the better intuition you have. The same as playing guitar. The more you play, the better you do. Anyway, so it's but there are some particular situations when I know the forces are conserved. First of all fundamental forces are conserved, right? And second, all central forces are always conserved. And all one-dimensional, but I'll talk about it later. So there are some specific cases when I actually don't even need to look at things, and I will know that the force is conserved. But otherwise, if I cannot prescribe that force to any of the fundamental forces, and the force is not central or 1D force, then I actually have to check.
But I guess the orientation of the path would matter. Like, for example, we were talking about like the electric field problem, where since that is that's a fundamental force, and if there wasn't any other like non-conservative forces playing a role, I guess the orientation of the path would play a factor.
No. That's it. It's a fundamental force. We know that it's conservative. That's it. It does not, then the result will not depend on path.
Even if with the electric field having like different directions at different points in space?
That's exactly the whole statement. It will not, it's a theorem. It will not depend on path. Period. It does not matter. The orientation of the path doesn't matter. How I draw that path doesn't matter. I'm going a bit ahead of myself, but for electrostatic force, you have force field, which is force field lines of this one, right? Right? So it doesn't matter if I move, if I take the path, for example, like simplest, I want to go from this point to this point. One way of doing of computing the work of electrostatic force is to take this path, right, along this line, and I'll get and it's the easiest one to do, and I get the number for work. But if I now don't want to live easy and happy, and I want to do a more complicated story, more complicated path for some reason, I don't know, I can go any path whatsoever and compute, because that tells me what to do. I can compute work which is done by electrostatic force along this path. The theorem tells you that work which is computed along blue path will be equal to the work which is computed along the pink path. It's a theorem. There is no way around it. Okay, that makes sense.
But the fluxes would be different since the areas would be different.
Flux through what? Let's not go ahead of ourselves.
With the loop that we just created, I guess.
First of all, for that loop, the flux doesn't matter, and in this problem, and But anyway, it says that you're trying to do something which is you're trying to do. That's always the problem. Students try to always think too complicated. I need to compute this. That's all. Right?
Yes.
That's my definition of work. Is there anything about flux here?
No.
Exactly. So I need to compute this. I need to take that path, split it on pieces, compute this one. Take this path, split it on pieces, compute the work here. That's all. And the theorem tells you that this work will be equal to this one. You don't need to know anything else. You like invent some fluxes, something else. Everything is here. Those definitions are complete. That's what the beauty of math is. That well, you know what to do, you do it. You have a theorem, it works. That's all. So don't overcomplicate things. Really. I mean, compute it. That's all. And now I will do it just in a second. All right. So again, that typically that situation that in this case, when you don't know anything about the forces, so let me write now the full definition, that work equals integral over gamma f dot dr. And again, I consider there is a force field and there is some path gamma, and I compute work done by that force along this path. So that work depends on gamma and depends on the force field. So that's work, right? Now, it does depend on gamma. In general situation, it does depend on gamma and so forth. However, let me assume that I know gamma and I know force field and everything, right? And I want to compute and now what I assume is that my motion, that this is a total force which acting on my particle, right? It includes like my force which I apply to it when I'm moving it around and so forth, right? Gravity, electrostatics, whatever. It's a total force. So the particle is moving. Well, let me write it like this: dv over dt equals f, and this is the same f as this one. Okay. So it's total force. Here in this equation, it is a total force. So it is a total force here. So I compute work, total work which is done on particle. And now let's imagine that I also know somehow the trajectory of the particle. Remember that the particle is now moving according to this force. So it's moving along some trajectory, and I assume that I know that trajectory. Right? Then I can compute that integral. Right? So let's do that. Because now what we know the force, right? We can substitute it here. So it's integral over gamma, and then what I have is m v. That's it, right? Oh no. M dv over dt, and here I have dr. So, right? Well, because my motion is due to that force, then I can substitute F equals m here. Now, I'll do the following trick. Instead of dr, I write that this is dr divided by dt and dt. Right? You see, dt cancels out, and only dr stays. Right? But then what I have here, dr over dt, dr over dt is exactly my velocity. So I write that this is v. Right? So what I have here is something. So velocity depends on time along the trajectory. So what I have here, like let's say y prime y, right? That sort of combination. Derivative times the function itself. And we know that this is nothing but m over 2 dv squared over dt. for any combination like that is just 1/2 y squared prime. That's exactly what we do. Here 1/2 and derivative of square. Right? But now what I have here, well, let me rewrite it a little bit. I write this is integral over gamma, and then I have dmv squared over 2 dt dt. Right? But this is a full derivative, right? An integral over the same thing as here. So dt cancels out, and what I have is dmv squared over 2. So what does it mean? It means that I travel along the path, and I add increments of mv squared over 2 at each point. Right? I add increments. So the total when I go from final point to initial, what I will have is the initial is the final mv squared final over 2 minus initial total change mv squared over 2. Right? That makes sense?
Yep.
So this is kinetic energy, just you know that, right? This is initial, right? And so this is final kinetic energy minus initial kinetic energy. So what we then find here is I think it's called work energy theorem, something like that. No one really uses it. So for any, if I can again, I want to emphasize like subtle points here. I can compute if I know that force field and I know some path along it. I can compute that integral for any path and any force, right? But if my motion happens due to the very same force, so this is a total force which acts on the particle, then I can find out that in this situation, that work which is done by this force, the total force, will be equal to the change of the kinetic energy. Right? So if I know kinetic energy at final point or change of the kinetic energy at final point and kinetic energy at the initial point, then of course I can that the work which is done by that force along the trajectory when my particle is moving will be equal to the change of the kinetic energy. Right? That makes sense? And it doesn't depend on what kind of force. It can be me. I'm not conservative force. So it's even I am moving the particles that I am applying some force to it. Then the F must include my force which I apply to the particle also. Okay, that makes sense.
Yes.
Yeah.
So this is sort of work energy theory. But now let's tell you that it's completely useless in majority of the cases, simply because you see that, well, if I know initial and final kinetic energies, I do know the work which is done by all the forces we checked on the acted on the particle when it was moving along the trajectory. And that is the only thing which I can compute. Right? If I know initial final kinetic energy, I can compute the work. But why would I need it? It's if I'm interested in how things are moving, then what does it tell me? There is some work. I mean, what do I do with that? Because work is because I cannot do anything with that. This is already just a number. It depends on path, right? So it means that here, in order to be able to compute it independently, to check, to find, for example, find the final velocity, right, from this equation, I need to compute work independently. But in order to compute work, I need to know path.
Yes.
But in order to know, but that path is a trajectory of the particle. In order to find trajectory, I need to. It means that I have already solved the full equation. Then I don't need all these tricks. I already solved this equation. I know velocity at every point of time, not just in time. Right? So it means that it's actually quite useless thing in this case. Unless this work, this integral, does not depend on gamma. Then I can compute this work. Just choose, if it doesn't depend, if this integral does not depend on gamma, I don't need to know trajectory. I can use whatever path I want to compute this integral, right? So here's my trajectory, here's my initial point, here's my final point, and I just compute, and there is some force field here, and I just compute work along this path. And if this force is conservative, meaning that f, exists some function u, right, such of x and y, such that f x equals minus du over dx, and f y equals minus du over dy. Right? Or if I don't know that, if dfx over dy equals dfy over dx everywhere, then such function does exist, right? And if it exists, then this integral does not depend on path. So if I have just a vector field, all I need to check those simple derivatives. I need to take derivatives and check them, and that's it. That's the easiest thing to do in the world. That they equal to each other. Right? And if they equal to each other, then function u does exist. And if it exists, I can compute this integral along any path. And if I can compute it along any path, well, I choose the path which is most convenient to me to compute it. Right? Just like with that electrostatic problem. So instead of going through this pink line, right, which was here before, which will be a difficult calculation with some electrostatic, when I have some electrostatic problem. That's a difficult calculation to do. I can do a very simple calculation, just go straight. And the work will be the same. Okay? That's the power of this theorem, that if my force field is such, it means that the force is conservative, then the function u exists such that fx is a derivative of u over x and fy derivative of u over y. And then I can compute this work along any path whatsoever. Okay, that makes sense? And then, of course, I can, if I know my initial point, I know my initial velocity. So I know point A in my initial velocity. It means that I know the initial kinetic energy. I can compute work of that force field along any path. I don't need to know anything about the motion of the particle. All I need to know is just force everywhere. I compute that force, I compute that work, right? And that doesn't depend on gamma anymore. And then I know this, so I will know the final velocity. Does that make sense?
Yeah.
So that's why it's so important to have conservative forces. They make things a lot easier because you can choose whatever path you want. You don't need to know to solve this equation before you compute and work. You just can compute it by any path, whatever. Okay? So that's why I was describing all these constructions last lecture. All right. Now, but let's think that actually we not only know that the function u exists, but we actually know that function u. So that it means that fx equals du over dx and minus du over dx, and fy equals du over dy. And by the way, if you have 3 dimensions, then you consider the same thing. Like then u depends on x, y, z, and you just continue going. Fz equals equals minus du over dz, and if you have 2500 dimensionality, you keep going. Right, but in order to check if your force field is given to you, in order to check if such function actually exists, right, what you need to do is to check all cross product, all cross derivatives, sorry. Right, so if you have 3 dimensionalities, that it will be x, y, right, and here y, x, then it will be x, z, and here it will be z, x. And it will be z, y, and y, z, right? So it will be 3 different conditions which you need to check, and all of them must be satisfied. And if all of them are satisfied, then your force is conservative, and such function it does exist. Okay, but still, it's a very simple thing to do. I mean, you just take derivatives. There is nothing simpler in mathematics than taking derivatives. All right, so let's imagine that now we not only we know that this is satisfied for our force field, but we actually figure out what the function u is. And so then let me again start with computing what work of the force is. And now I know that the work of the force does not depend on path. It depends on the initial and final positions. And what I have here, f dot dr. All right, that's a definition. That's a definition of my work. But I just know that it doesn't depend on gamma. But what's written here? What's written here? I just use the dot product, right? And I use those definition of my forces. So what I have is minus du over dx, x component of the force, times dx, right? Plus y component of the force, and dy times dy. Right? That's the definition of a cross product. Now I look at it and I see that this is a full differential of function u. So that equals to minus integral du. Right? So doesn't matter which path I go, what does it mean, right? What does that actually mean? I go from point A to point B, from point B, right? Along some path, doesn't matter. And I take the increment of my function u here on this part. Then I take the increment on my function u here, right? Increment, right? So, and then I sum them up. So increment plus increment plus increment plus increment plus increment, and so forth. So what I will have at there? Well, I will have the total change of the function between the 2 points. So what I have here, so it's the initial and final point. I have, let me use the same. So it's initial point and final point. Right? So what I will have here is minus, and then I have u at final point minus u at initial point. Right? Now I have 2 different computations for the same value. In case of conservative forces, what I have is here is minus uf plus ui initial, right? But they must be equal to each other. I computed the same thing 2 different ways. So they must be equal to each other. And what I will have then, is k final minus k initial must be equal minus u final plus u initial. Right? Now let me take all initial points on one side and final points on the other side. What you will see is k initial plus u initial equals k final plus u final. So kinetic energy, and this u function u is called potential energy, And what I have here is the sum of the kinetic plus potential energy. So it's total energy. Total energy at initial point equals total energy at final point. So the energy is conserved. That's why the force is called conservative force. Right? So, but you see that the initial final point can be any point on trajectory. I can stop my motion at any point. And I still, for any of those points, I must still have the same. E initial must be equal to E final. So it means that energy actually does not change with time at all. It is the same number. I can compute at an initial point, and during the motion, the total energy, kinetic plus potential energy, will always be the same as in the first moment of motion, in my initial point. Right? Does it make sense?
Yes.
This is called energy conservation law, of course, you know that. But again, I want you to understand that it's coming from conservative forces, and it's coming from that neat trick that work does not depend on gamma. By the way, that work does not depend on gamma means that work on any closed path equals zero, right? Because if I have closed path, I can take this as my initial point, this is my final point, right? And work along this must be equal to work along this path, right? Because work does not depend on the path. But then, if I now take the whole path, I see that this is this path, work on this path, minus work on this path, because I go here the opposite direction. But they're equal to each other. So the sum of W plus minus W will be equal to zero. So the work along every closed path equals zero. And that's why you cannot get energy out of nothing. Just returning back and returning back to where you are. So it's called energy conservation law, and the fact that all our fundamental forces are conservative forces means that energy is conserved, and we cannot get anything for free. It's unfortunately that's energy conservation, right? Now I want to point out one more thing in there. There is a deeper reason for the conservation of energy. And that's actually quite an interesting reason for that. The reason for conservation of energy, deep reason, is a time translation invariance. The fact that that no matter when we do experiment, we can do some experiment today and repeat it tomorrow. The answer will be the same, right? So it's this is called time translation invariance. That if I translate all times, then the answer will be the same. That is some sort of a symmetry, right? So that it doesn't matter when I do it. And that's exactly, it's called time translation invariance, and that's the reason why energy is conserved. It can be traced to that, and but in different ways. The same as momentum conservation can be traced to the symmetry of translation invariance. Translation invariance means that it doesn't matter whether I make the experiment in this point of space or in this point of space. The answer should be the same. So that symmetry, that I can translate everything, and all experiments will go the same way, leads to momentum conservation. So that actually those energy momentum conservation has quite deep reasons. The angular momentum conservation also has the same reason. It's when you do experiment in this orientation, then I do experiment on different orientations. The answer must be the same. That leads to momentum. And there is, again, it's quite deep reasons. They all come under the name of Noether's theorem. It's Emma Noether. He was a mathematician in I don't know, in 19th century, I think, and one of the best mathematicians, mechanics back then. And it's a completely amazing theorem, a set of theorems, which is absolutely amazing. I don't know how to describe it. But they're a little bit more technical. I cannot Now let me. So that's conservative forces, right? And as was already, I was asked that what is. Oh, just a second. There are a couple more things which I want to do. And before that, right? So you see that the thing which is in equations of motion is force, right? Now our U, that energy, is defined through derivatives. This is something which we can measure. We invented potential energy in order to describe things, to solve our equations easier. Right? And it's defined through derivatives only. Only derivatives of potential energy matter, right? Because only derivatives is force, and only force is an equation of motion. So it means that if I take U, for example, and add any constant to it, this equation will not change, right? So if I add any constant to U, to the potential energy, it will still describe exactly the same force. So that constant is immeasurable. So the function potential energy is defined up to a constant. I can always add a constant to a potential energy. So for example, in electrostatics, you know that potential energy is kq divided by r, the distance between them. I can always add any constant to it. And everything will go through, everything will work, and no result of any measurements will depend on this constant. So you can choose this constant any way you want, if it simplifies your calculation. And in this particular case, in electrostatics, it's usually defined such that this constant is zero when two points are very, very far away from each other. And then that's what you have. But in reality, you can define it any way you want. Any constant, any constant. And that's exactly the same as potential energy, right? You know that potential energy equals mgh, right? So what is that h? Answer me, you know this.
It's a height.
Height with respect to what?
The ground or where you're observing?
So it can be different things. Which one do I choose? Right? I'm observing, I'm on the fourth floor right now. Ground is way below me. So which one do I choose? Which one is I plug in here?
It depends on the scope of the problem, like where you would want to start.
How my particle knows where I want to start? It has no brain. So the correct answer, that's exactly what I was just talking about, like for 10 minutes. That's exactly the same thing. It does not matter. The only thing matters is that you have chosen your 0h somewhere, once and for all. You want to measure it from the ground? Measure it from the ground. You want to measure it from the floor? Measure it from the floor. But all the time you measure it from the same point. You have chosen one point at which your potential energy is zero. And you can choose any point you want. The answer will not depend on it. Because at the end of the day, if you remember, the only thing which matters is the change of the potential energy. Potential energy by itself never appears in any calculation, in any final result. It only change of the potential energy which appears. Right? But the change of the potential energy does not depend on where you measure that h from. Because it's never h, it's the change of h which appears in all the problems. And change of h doesn't depend on where you start measuring it from. That's exactly what I was trying to describe. You can always add any constant to a potential energy. All right. Unfortunately, I have to hurry up, and because it's something which you need for homework, what I'm trying to describe now. So, again, I need to again come back. This, by the way, it says, remember that the work does not depend on path. You actually, majority of you, very many of you, I'm not sure, the majority are electrical engineers. So you know Kirchhoff's rules, right?
Yes.
Yes.
That's exactly what it is. Remember that if you count the potential differences along any loop in the circuit, you must return back to where you were, to zero, right?
Yeah.
That means that the potentials which you computing, it's a work which is done by electric field when you move an electron along that loop. That work must be zero. This is the reason for that is that electrostatic forces are potential forces, conservative forces. That's exactly that's just what it is. I mean, you move an electron along the loop, and your result must be zero. That's what I've done for F dot PR. That's Kirchhoff's law. That's Kirchhoff's rule right there. It was written just on a continuum limit, not on the one loop. Right? And the second thing is that you always write it where is the ground is, right? And it really doesn't matter where you put the ground on your circuit. Right?
Correct. Yeah.
But that's exactly what I just told you about, that you always choose where your potential is zero. At one point, you choose that in this particular point, I will call potential energy to be zero. And that's where you put the ground. That's the definition of the ground, is exactly what I just described mathematically. Okay? All right. Unfortunately, I have to move forward. There is one case where is that we know that all the forces are conservative. All the forces which depend only on coordinates, right? Depend only on coordinates. They must not depend on velocity like friction force. If forces depend only on coordinate, and we are in 1D, so there is only one coordinate somehow, right? Then all forces depend only on x, right? And I don't need to write a vector here because force can be either positive or negative, and that's already the direction, right? Then for any such function, I can always write a function u, which is minus integral from some initial function. Doesn't matter because it's one point where it's zero. To x, let me write it, u of x, u of this x equals f of x prime dx prime. Right? If I write such function, if I know f of x, I can always take this integral and write this function, a function of the upper limit. Then, according to the theorem of calculus, f of x equals minus du over dx. Right? So for any one-dimensional force field, any one-dimensional force field is always potential force, always conservative force. And I always know how to find that function u. So every force which depends only on coordinates in 1D can be described by potential energy, u of x. So instead of giving f of x, I give another function which is u of x. Right? Does that make sense? But then, look what happens. You see, it's a conservation law. In mathematics, they call those conservation laws first integrals of the equation. This is our differential equations, and one of the first integrals of the differential equations is the potential total energy. It's conserved quantity, and if you remember that every time you have a first integral, you of the potential of the differential equations, you can decrease the degree of your differential equation. But in 1D we have only one second order differential equation. So if we now use energy, we can write a first order differential equation. And that's a simple thing to do, right? So we have our x, right? So this is 0, and our particle is moving here, and its kinetic energy is mv squared over 2, and potential energy is u of x, which we just figure out, right? Just integrating the force. And this is our total energy. Now, total energy we can always find from initial conditions, right? The total energy is given by mv naught squared over 2, right? Initial velocity. plus u of x naught. Right? The initial potential energy. So we know the total energy. We must be given initial conditions in order to define our motion. So we know our energy. But let me write then what is velocity here. What I have here is m over 2 dx over dt squared. Right? So now let me take this u, move it over here, and what I have is dx over dt squared equals 2 over m, and here I have e minus u of x. Right? You see it? Just move you here and put it up. Now let me take the square root of both sides. Now let me take dt over here and everything else over there. What I will have is this dx divided by square root of e minus u of x. Then I have m over 2 square root equals dt. Right? That makes sense?
Yeah.
Now let me integrate this equation. So what I have is the integral here, which is coming from the initial position, my initial condition. And remember, E is also given by initial condition. Then I have this integral up to x at some point t, which I don't know yet, but let's put it there. This integral must be equal to the integral of dt from my initial time t naught, where my initial conditions was given, times time t, where my particle is at point x. But that integral I can easily take and write this is t naught minus t. No, t minus t. T minus t naught. And of course, when I take the square root, I have plus minus. Or let me write it from x naught to x function of t and plus minus. Right? Now, what you see that you know everything under this integral. So you can take this integral, either from using mathematics or your brain, whatever. Right? Take this integral. You will have some function here of the upper limit x of t, and you have the same t here. So if you now take this function and from that function express x as function of t through t, then you know the position at every point of time. So we have solved every one-dimensional problem, every one of them. Let's do it for one example. One of the examples will be in your homework. It isn't your homework. But let me consider the situation of a spring, right? When we have F equals minus kx. The potential energy, which describes this force, is U equals kx squared over 2. So now I just take this as it is and write my and I need initial conditions. So let's write the initial conditions that x at t equals 0 and v at t equals 0 equals v naught. Then from here I see that my kinetic energy and potential energy at t equals 0, right? I need to put x equals 0 here. It is 0. And so my total energy equals m v naught squared over 2. Right? So now I plug plug everything in here. And what I see is that it's t minus t naught. That's the initial point of time. My initial point of time is 0. So I don't need to plug anything. Plus minus square root of m divided by 2 square root. And then I have integral from x naught, which is 0, to x as function of t, which I want to find later on. And then I have dx, and here I have m v naught squared over 2 minus my potential energy. Potential energy is this one, k x squared over 2 squared. That makes sense?
Yep.
So now if you
That makes sense.
So you see that this is a function of just x, right? X squared. This is the integral dx over square root of something minus something times x squared. That integral can be taken, and you will probably know what it is. That's the arc sign. And from so you take this integral, and then from it in this integral you will have to substitute 0 and x of t, right? Then you take this expression and find what is solved for x of t. If you do that, what you will get is the following. Yeah, x of t equals v naught divided by omega sine omega t, where omega equals square root of t divided by. That's your standard oscillator. So instead of solving that equations and blah, 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 you can just simply take the integral. You can give it to mathematics, it will take it, it will give you the answer. Right? Does that make sense? So I just solved for you every one-dimensional problem. But we can do even better. So that solution, right? It's, so from now on, if you have one-dimensional problem and your force is conservative, it means that force depends only on coordinates. It does not depend on velocity. You plug it in here, in this equation. You take this integral, and you have complete solution. Okay? Does that make sense?
Yes.
Yeah.
And so for the homework or anything like that, we can just put in that equation. We don't have to have the proof for it.
No, it's I gave it to you, right? So you just
Okay, just making sure. Thank you.
It's a good thing to actually derive it. I mean, it's a trivial calculation in reality. If you do it, it may look scary, but if you do it once, you will see that it's actually an extremely trivial thing. All right, but now let's see that what else can we do from this picture? We know that m v squared over 2 plus u equals e, right? And u depends on x, of course. So let's see what is let's draw the function u as function of x. And I don't know what it is. It's some function. It's well, let's just draw something. Okay. So this is my u of x. This is my u of x. Now I know that this is a constant, right? Energy is total energy is a constant of motion. So let me just draw that constant. It's a constant, right? No matter where my particle will be during my motion, it will exactly, so whatever my particle, whatever the coordinate of my particle is, E will be exactly the same. So I draw it just a straight line. So this is E. Now I look at this formula, and I write it the following way, that m v squared over 2 equals E minus u of x. Right? This is what under the square root was. Right? But now, look at this. This is v squared. This mass is positive. V squared is definitely non-negative, right? Well, 2 is also positive. So this is a positive number. But this can be either one. So it means that motion only possible if this is positive, well, this is not negative. Right? E minus u. Now I look here and I see E minus u is positive here. This is E, this is this point, right? This is E and this is u. So it's positive. But it is negative here. Right? So it means that the particle cannot be here at all. This is prohibited region of the motion. For a given E, right? If I increase the energy, increase it here, then I can increase it up here. The energy is given by initial condition. Right? So to change in initial conditions, I can move that E up there, and then my particle can move up there. But if for that particular initial condition, for that particular E, the motion here is impossible. The motion here is possible. But the motion here is impossible. Here is impossible. But this one is possible. Right? So my particle can move from this x1 to this x2. Right? Does that make sense?
Yeah, that makes sense.
Now, remember that there was plus minus sign in the formula which I wrote before. And that's exactly the problem why it appears, because I take a square root in order to find velocity. Right? But square does not know about the direction of the velocity. Is it positive or negative? And there is no way to tell. So this is something which I need to tell from my initial conditions, from my understanding what's going on. This is a strange minus sign, plus minus sign there, but it works in all the problems. And in particular here, it means that the particle is a positive velocity or negative velocity, right? As you remember, the plus minus sign is exactly velocity, positive or negative. And that's possible. Both cases are possible. So, but then what happens at this point? Well, in this point, kinetic total energy, the big one, equals the blue one, right? There's the potential energy. This energy equals this energy, so the kinetic energy is zero. It means the velocity is zero. Those are called stopping points. The particles have zero velocity. Velocity is zero, but remember that force is a gradient of potential energy, right? So the force here, the gradient, the derivative is not zero. So velocity is zero, but the force is not zero, so acceleration is not zero. So what happens here then is the following: the particle is moving up to the stopping point, then it switches. Its velocity is zero, so it can be minus zero then, right? And it goes here, and it then reaches this stopping point, switches the velocity, direction of the velocity goes zero. So the particle goes back and forth. So it's a periodic motion, right? And now you can see that in 2 dimensions in conservative for conservative forces, there are only 2 types of motion which are possible. Is a periodic motion, or the particle, for example, here, it can come here, stop, turn around, and never stop again because it goes down and down and down and down, right? So there will be no stopping point. So it's either periodic or unbounded motion, and there is no other possibility in 1D. In 3D and in 2D, there are plenty of other possibilities. But in 1D, there is either periodic or the unbounded motion. But moreover, from this picture, we actually can find what's the period is. So let's figure out what is the period from going from here to here. Well, we know that time equals integral, and of course I forgot which is where the mass is. Yeah, mass over 2. M over 2 square root integral, and let's start our motion from x1. x1, and let me keep this as it is. And it's dx divided by e minus u of x square root, right? That was our initial, and here is x function. So my particle goes from here up to here. So let's put here x2. what is here, what this t is exactly time which it takes my particle to go from here to here. And exactly the same time will be from here to back. But that's exactly our period. Right? So the period of that motion will be equal to twice this integral. That's all. So for any energy and any u, what we need to do? We need to first solve the equation. Those are these points, x1 and x2, right? So from here, we'll find x1 and x2. And then all we need to do is to compute this integral. And that will give us the period of motion for this particular energy in this particular area. Okay. And the classical particle cannot penetrate in the prohibited region. Quantum mechanical can. But classical particle cannot penetrate inside here. It just will go back and forth here. All right? So this way you can solve every one-dimensional problem. Just simply starting from energy conservation. All right, that's it for today. And any questions? Any questions? Well, okay then. And I have office hours in 1 p.m. So if you have any questions but you're afraid to ask, just stop by.
Professor, so you said classical mechanics, the particle cannot enter the prohibited region, but so in quantum mechanics it can?
Yeah.
Okay.
Yeah, it can, because in quantum mechanics there is no, you see that quantum mechanics is a funny thing, and I'll talk about it at the end of this class about quantum mechanics. But quantum mechanics is a funny thing. You cannot define the position of a particle there. So the position of a particle is a weird thing in quantum.
The Heisenberg uncertainty?
Yes, exactly.
Okay.
Yes.
Thank you.